Welcome to our simple guide to making your very own microfluidic device. This video is a culmination of our experience of making microfluidic devices for our master's project at Queen Mary University of London. We have tried to include all of the practical tips we have picked up over the course of our project to help you avoid the same pitfalls that we identified during the manufacturing process. Hopefully this will make your life a little bit easier.
This process can be split into two main sections. Firstly, using soft photolithography to create a negative master pattern on a silicon wafer substrate. Secondly, using this master to create a PDMS microfluidic device. Let's start off with soft photolithography.
The first step is to ensure that we have a hydrophilic surface on our silicon substrate. For this, we used oxygen plasma treatment, which raises the surface energy of the substrate. This is essential to promote the adhesion between the silicon wafer and the photoresist on your final master pattern.
Treat your silicon wafers in an oxygen plasma machine for a sufficient amount of time to improve the hydrophilicity. We found that a treatment time of 10 minutes at 0.3 millibars gave good results. The hydrophilicity of the silicon wafer is defined by the contact angle of a water droplet. You can do a simple visual test by placing a water droplet on the surface of the wafer. If the droplet is flat, your surface is hydrophilic. Here you can see the difference between a treated and untreated surface. Notice the dome shape on the untreated surface.
Oxygen plasma bonding should give you a clean wafer. However, if you see any dirt or dust on the surface of the wafer, you can clean it using deionized water and isopropanol. It is extremely important to have a clean wafer to avoid defects in your final master pattern.
Step 2 is to spin coat the silicon wafer with photoresist. There are different photoresists available on the market to suit your needs. We chose SU8 2100 to create channels with 100 micrometers height. At this point, it's a good idea to download the datasheet for your photoresist. A lot of useful information is found here. You can find this on the manufacturer's website.
Place the silicon wafer about its center of rotation in the spin coater. This is important to get an even coating of photoresist. A simple way to manually center the wafer is by rotating it using your finger on the edge of the wafer. You'll be able to observe if the wafer is rotating unevenly. Adjust the position until the wafer is centered.
We can then set the spin speed, which determines the height of the coating. Consult the photoresist datasheet for guidance on the recommended spin speeds. You may need to adjust the values from the datasheet depending on your equipment. We used 10 seconds at 500 RPM and 30 seconds at 2300 RPM to achieve a coating height of 100 microns.
Having set the spin speed, we can apply the photoresist. The best method we have found to do this is to load a glass syringe with photoresist and use this to dispense onto the wafer. Do not use plastic syringes, as the photoresist can react with the plastic, creating unwanted residue. Make sure that there are no air bubbles in the syringe, as this will cause defects on your coating. Apply the photoresist onto the center of the wafer and keep the tip of the syringe in contact with the photoresist to avoid bubbles, but make sure that the tip is clean. We found that 4 milliliters of photoresist worked well on a 4-inch diameter substrate. A good tip here is to clean the lid of your spin coater using acetone to avoid any contamination of your photoresist. Then run the spin coater. It is best to do this whole process as quickly as possible to ensure the best quality coating.
Step 3. Soft baking the wafer. Soft baking is required to evaporate some solvent. This improves adhesion to the substrate and allows the UV photomask to be applied in the next step without sticking to the photoresist. You can refer to the photoresist datasheet to get recommended times for your product. We found that 5 minutes at 65 degrees followed by 20 minutes at 95 degrees worked well. Allow the wafer to cool to room temperature before the next step. The convection within fume hoods can cause too much solvent to evaporate. To avoid this, you can use a simple aluminium foil to cover the wafer. This also serves to keep the wafer clean and maintain the desired temperature.
Step 4 is the UV exposure to cure the photoresist. You should already have a UV photomask with your designs printed on them, like this one. Several guides are available online to help you create your designs on AutoCAD software. Clean the photomask using isopropanol and distilled water. Remember, any dirt on the channels on your photomask will show up on your final design. place your photo masks onto the photoresist using a mask aligner. There is a correct side for the design which you will be able to tell from experience. The easiest way to make sure you place the right side down is to add letters or numbers around your channels when designing the photo mask.
A good tip at this stage is to cover as much of the unused areas of photoresist as possible using blank pieces of UV photo mask. This will prevent unwanted regions of cured photoresist from forming, as shown here. During the developing stage, these regions can make it difficult to get well-developed channels. As they say, prevention is better than cure. The recommended exposure dosage can be found on the datasheet. Based on this, we calculated that an exposure time of 30 seconds was sufficient for us.
Step 5 is the post-exposure bake. This evaporates more solvent and improves adhesion of the photoresist to the wafer. It also reduces stresses by promoting mechanical relaxation of the channel. Refer to the photoresist datasheet for timing guidelines. We found that 5 minutes at 65 degrees C followed by 12 minutes at 95 degrees C worked well. If your design was sufficiently exposed, the pattern should become visible after 2 minutes at 65 degrees C. If this is not the case, then your wafer may be underexposed. Then we can move on to developing the channel.
Developing a high-quality channel is challenging. Final results are dependent on your own skill and judgment if you are using a manual developing process. The photoresist datasheet has guidelines on timings for SU8 developer. Timings are dependent on the width and height of your channels. We found that for our designs of 50 by 100 microns, the timings in the datasheet resulted in significantly overdeveloped channels. It is useful to start with a basic understanding of the substances we are using to develop our channel.
We have used SU8 developer, acetone, isopropanol and distilled water for development. Consider a scale from 1 to 10, where 10 is a substance that quickly and effectively removes SU8 and 1 is a substance which does not remove SU8. As expected, SU8 developer ranks a 10. This is our primary developer and it will remove SU8 quickly and effectively. Acetone ranks a 7. It also acts as a developer. Given enough time, it can remove SU8 all the way down to the substrate, but it does not act as aggressively as SU8 developer.
Isopropanol ranks a 3. This is significantly less effective than acetone at removing SU8. It is useful for removing small amounts of SU8 without damaging the channels. Finally, distilled water would rank a 1. It does not develop SU8, but it can be used to remove other solvents and residue. It is also useful to dilute the other solvents to reduce their aggressiveness if some subtlety is required in developing.
Just a word of caution before we start. It is better to underdevelop at this stage than overdevelop. You can always improve underdeveloped channels, but an overdeveloped channel means that you have to start this whole process again. If you are unsure, be conservative with timings.
Now we can start developing. Start by pouring a small amount of SU8 developer into a glass dish. The amount should be just enough to submerge the silicon wafer. Do not use a plastic petri dish, as the developer will react with the plastic. Place your wafer into the developer and start the clock. The developing time is largely dependent on your channel dimensions. Our channel was 50 microns by 100 microns in height, and we found that 3 minutes 30 seconds was a good amount of time to leave the channel in the developer. Then take out the silicon wafer and give it a quick rinse with developer. You should be able to see the photoresist streaking off the wafer.
Next, we recommend that you use isopropanol, as this gives you a good indication of how well developed your channel is. Notice the large amount of white substance on the surface of the wafer. This is photoresist. If you see this, it means that your channel is underdeveloped. If the amount of substance is substantial, you can put it back into the developer for about 20 seconds. You should see the white substance clear away. If the white substance remains, you can use acetone to remove it. Remember, acetone acts as a developer, so be careful not to overdo it. If required, you can simultaneously use distilled water and acetone to dilute the solution and prevent overdevelopment.
Use isopropanol again. The white substance should be significantly reduced. This means your channel is almost developed. Pay close attention to the channels. They should be darker than the substrate. If they become the same color as the substrate, then they are overdeveloped. Finally, use distilled water to wash off any remaining residue. Dry the silicon wafer using a nitrogen gun. Be careful not to overdo the nitrogen gun, as the channels may fly off. Let the wafer cool to room temperature.
Check the channels under a microscope. Look for the wall quality and any defects and blockages. You may see crack formation in the channel, particularly at corners and junctions. These can be removed by hard baking at 150 degrees Celsius for 5 minutes. Now you have your silicon master wafer ready to create your PDMS device.
Part 2. Now we can move on to the second phase of the process. The first step is to apply the PDMS layer. We used commercially available silicon elastomer and curing agent to create our devices. Silicon is used due to its inert properties, ease of manufacturing, and excellent optical transparency. Mix 10 parts of elastomer to 1 part curing agent. For devices 5 mm thick, approximately 30 milliliters of silicon was sufficient to cover a wafer of 4-inch diameter.
Place your wafer in a petri dish to contain the PDMS while it cures. Alternatively, you can use aluminium foil to contain the PDMS, as shown here. Pour the PDMS mixture onto the silicon wafer, making sure that the wafer is on a flat surface. The chemical reaction in the PDMS creates bubbles. You can get rid of these bubbles using a desiccator and a pump. If you do not have access to a desiccator, leave the PDMS at room temperature for approximately 1.5 hours. After this, place the silicon wafer in an oven at 65 degrees to cure for approximately 3 to 4 hours. You should leave the PDMS covered to avoid any contamination.
Once cured, carefully cut out the PDMS device into rectangles roughly the size of the cover glass you will use. Our cover glasses measure 35 by 65 mm. Make sure you leave approximately 5 to 10 mm on each side of the channel to prevent your channels being too close to the edge of the cover glass, as this may eventually cause a leak. You should take care now to keep the PDMS device clean, as any contamination may result in blockages in your channel.
The next step is to punch the holes for the inlets and outlets. We use the standard 0.8 mm hole punch to create the holes. The holes should be punched from the channel side and should penetrate all the way through the PDMS device. So be careful not to make your PDMS too thick in the previous stage, as your hole punch may not be deep enough. We found that it was preferred to punch the holes on a hard, flat surface to prevent tearing of the PDMS on the top side of the device.
Step 3. We used oxygen plasma bonding to seal the channels with a cover glass. Place the cover glass and the PDMS onto the tray for the plasma bonder. We need to treat both the PDMS and the cover glass to achieve bonding. It is useful to place the device and cover glass on a few microscope slides to make handling the cover glass easier for the next stage. Remember, we need to treat the channel side of the PDMS device, so make sure this is facing up, as this is what will be treated. Make sure the channels and the cover glass are clean. You can clean them with distilled water. We used oxygen plasma treatment for 1.5 minutes at a pressure of 0.4 millibar. You can use other gases such as air for treatment, but the parameters may change.
The surface treatment effects last for approximately 10 seconds, so you must work quickly for the next step. Remove the device and cover glass and place the treated side of the cover glass firmly onto the treated side of the PDMS device. Use your fingers to get rid of any air bubbles. Now you have your sealed channels. The strength of the bond is not at its maximum yet, so be careful with the device.
The next step is to insert the needles and tubes for your inlets and outlets. To seal the needles in the PDMS device, we used a 2-part epoxy resin. We found it best to apply a small amount of epoxy resin, about 3 mm above the tip of the needle. Make sure not to block the opening. Then insert the needle into the holes made earlier. Make sure not to push the needle all the way down to the cover glass, as this will block the inlets and outlets. Leave a small gap so that the particles can flow through the channel. Apply extra glue if required around the needles on the top surface of the PDMS to completely seal it.
A good tip at this point is to make sure the natural curve of the tubes points away from the channel. This will make connecting the syringe pumps during testing a lot easier. Then put the whole device into a drying cupboard at 60 degrees Celsius. Do not use ovens, as this may degrade your tubes. we found that leaving the device for at least 3 days significantly improves the strength of the oxygen plasma bonding and the overall durability of the device.
So now you have your completed PDMS microfluidic device ready for testing. We hope you found this video useful. Please leave your comments and feedback below.